In this video, we're going to discuss the alkylation of aromatic groups. So an alkyl group is any carbon-based group. So generically speaking, we could say R, and we can take a benzene or some derivative of benzene, and if we add an alkyl group, we will now have benzene with some R group on it. And there are a couple of different ways to do this, so we're going to break it down over the next couple slides. One way is the Friedel-Crafts alkylation. So the Friedel-Crafts acylation is something that we'll talk about in class, or maybe have already talked about in class. The Friedel-Crafts alkylation uses an alkyl halide. So as an example, we'll use T-butyl chloride, and this is done in the presence of an aluminum trichloride catalyst. And when we do that, we end up with our T-butyl group attached to our benzene ring. So that's the alkyl part. So this proceeds very much like the first step of the Friedel-Crafts acylation. This chlorine that's on my alkyl group is going to coordinate with the aluminum that has an empty p orbital in my Lewis acid catalyst, the aluminum trichloride. So it's going to make a Lewis acid base adduct, and we'll show that on the next slide. So now as an intermediate, I have this species. My chlorine is positive because it's donated some electrons, and the aluminum is negative because it's accepted electrons. And what it really comes down to is that this is a good leaving group, because what I'm trying to do is generate an electrophile for the aromatic ring to attack. So what happens is my leaving group can leave, and I end up with my tertiary carbocation plus my leaving group. So now my chlorine is going to be neutral, the carbon is positively charged, and I have this aluminum compound over here. So in doing this, what I've done is generate a really good electrophile. So an electrophile is something that likes electrons, likes negative charge. It has a full positive charge on it, so it would be a good electrophile for my aromatic ring to attack. So this is one example of how we can make a good leaving group that will leave willingly and leave a carbocation intermediate behind. From this point on, it's going to behave like every other electrophilic aromatic substitution that we've seen. We have a full positive charge on our carbocation there. Some pi electrons are going to come out and attack that. This would be my slow step because I'm disrupting the aromaticity of the compound. I end up with my tert-butyl group on and a positive charge. So this is my intermediate that is resonance stabilized. So I have these three resonance intermediates that stabilize the positive charge as it is rotated around the ring. And then what happens is that aluminum chloride source that I had from before, where I have the negative charge on this chlorine, can come and deprotonate so that I can regenerate my aromaticity. So what happens here is I've got a lone pair of electrons on the chlorine can grab the hydrogen. These electrons can fold back down to make a double bond, and then we'll kick the chlorine off of the aluminum with the electrons. So what I end up getting here, and this would be my fast step because it regenerates the aromaticity of the compound, is my benzene ring with the tert-butyl group on it. HCl is a byproduct from that deprotonation step, and then my aluminum chloride catalyst, which is regenerated. So it can go and react with another equivalent of an alkyl halide in order to make the electrophile, which is that carbocation, and do the whole process over again. So that's why we call it a catalyst. In truth, it actually doesn't work that well fully catalytically. You kind of need to put more than that in there. But it is regenerated as the process goes on, and the HCl is generally a gas at the temperatures that we have to do this, so it will go off, which makes it nice that you don't have to worry about separating that byproduct. So to make this reaction go, what you really just need is a good electrophile, and that carbocation is a really good electrophile, but there's more than one way to do that. So we could do the Friedel-Crafts alkylation, which we just looked at. We could also take an alkene like this, and we could add H+. Now H+ is generally H2SO4 because it tends not to react with anything else, the conjugate base. So what ends up happening is I protonate to get the most stable carbocation intermediate, and then that can act as an electrophile. So I could begin with an alkene under acidic conditions to generate an electrophile that could then react with an aromatic compound. I could also take the same derivative with an alcohol, and again put it in H+, H2SO4. If I put this in H+, I make water, which is a good leaving group, and I could generate my electrophile that way. So what I've done here is generate a good leaving group again, and that's what the Lewis acid catalyst helps to do in the Friedel-Crafts alkylation. So we can alkylate under these three different circumstances and all get the same product given these reactants that I've started with. So in summary, I could take this compound and under three different sets of conditions generate the same electrophiles. So we could take T-butyl chloride with aluminum chloride. We could take an alkene in the presence of acid to generate a carbocation, or we could take an alcohol in the presence of acid. And in all of these cases, you end up generating a carbocation intermediate like this, and that will react to give you your final alkylated product.